Most numbers we've seen so far are rational. Rational numbers include negative integers, positive integers, and fractions, as well as decimals. Now, the word rational comes from ratio, which means any rational number can be written as a ratio of two integers. So, ratios are often written as fractions, right? A number like 6/7 is a ratio of 6/7. And as a fraction, which can be converted to a decimal, it's a rational number because it can be written as a ratio, which can be written as a fraction, and all fractions can be written as decimals. So this is why most of the numbers we've met so far are rational, because they can be written as ratios, as fractions, as decimals, right? But not all decimals are rational. Many decimals are rational. The ones that repeat in a pattern and have that pattern go on forever and ever, that's a rational number, because any number that has a repeating pattern, even if it repeats forever to infinity, can be written as a ratio of two integers. So rational numbers come in various forms. They can be written in different ways, but still be rational. So you get all sorts of numbers in the rational set. For example, 1.05 is rational. And it's rational because it can be written as 105 divided by 100. 0.3333 recurring is also rational because it can be written as a third. And a half is rational because it can be written as a ratio of two integers, 1/2. 6 is rational because 6 can be written as 6/1. That's a ratio of two integers. So rational numbers have all got one thing in common, and that's the fact that every one of them can be written as a simple fraction, right? A simple fraction with an integer on the top and an integer on the bottom that's not 0. Okay, so here's a formal definition of a rational number. A rational number is a number that can be written as a/b, where a and b are both integers, but where b, which is the denominator, cannot be 0. So here is our formal definition. Basically, 3 types of rational numbers exist. All the integers are rational. They're rational because every single one of these integers can be written or rewritten as a fraction simply by placing 1 as the denominator. See, it even works for 0. Similarly, all terminating decimals are rational. So whenever you have a decimal that ends after a certain number of decimal places, not by you rounding it, but by it simply ending, then that number is rational. And that's because every terminating decimal can be converted to a fraction that has an integer on the top and an integer on the bottom. So 1.2 over 1, removing the decimal place and doing the same on the bottom, it gives you 12/10, which is the same as 6/5. See? So we end up having an integer on the top, 6, over an integer on the bottom, 5. The rest of these, even these complicated looking ones, can be converted easily to fractions by simply doing a similar thing. 5.689. How many times do we move this out? 3 times. 5.689 is equal to 5,689 over 3 zeros. And we can do a similar thing for both 3.72, negative 3.72, and negative 0.69245. Simply place the number over a certain power of 10 depending on how many digits are falling behind this decimal point. 1, 2, 3, 4, 5 here. That would mean minus 69245 over 100,000 is minus 0.69245. Finally, all repeating decimals are rational. So as long as there's a pattern in the decimal that repeats over and over forever, then it's also possible to write that number as a ratio of 2 integers. So here we have 0.0909090909. That 09 repeats over and over. That's a ratio of 1 to 11, 1 over 11. Here's another example, 0.333, which we saw earlier. It's a third. And 0.045045,045. It goes on, 045045 is a ratio of 5 to 111. Whenever we have a decimal that doesn't repeat in any particular pattern and never ends, then we have an irrational number. Such a number cannot be written in the form of a over b, where a and b are both integers. So these numbers now that do not repeat in a particular pattern and go on forever and ever, those are irrational numbers. They're the opposite of rational numbers, which can be written as a ratio of 2 integers, and where if they go on forever, then the pattern that continues forever is one that repeats in a predictable way. So irrationals don't repeat in any predictable way, whereas rationals, if they go on forever, will repeat in a predictable way. One very famous irrational number is pi, which we use when we're calculating the circumference and areas of circles. Pi, the measure of pi, or the length of pi, is 3.141592653, but that's not the whole of the number. That number, pi, goes on forever and it never repeats. So we always have to truncate, cut off some of the end numbers of pi. It's always written in an approximate way because it's irrational, doesn't repeat in any particular pattern, and goes on forever.